Okay, thank you. My apologies for running a bit late getting here. So this is work that takes place in both Wireless Foundations and the Berkeley Wireless Research Center. So Berkeley is organized around lots of little centers, and BWRC is where they look at implementation issues, so everything from circuits to antennas to protocols and so on. Wireless Foundations are a new group where we look at the information theory, comm theory, algorithms, and there's a lot of overlap. So for example, my student Mubarak is joint between the two centers. So he's half my student and half Bob Butterson's student. So this is the obligatory slide 1 about spectrum. Who here has not seen this slide? Okay, good. So skip it. So we all know there's a problem. Spectrum isn't being used properly. So what can we do about it? Yeah?
What is the green slide on the page?
Oh, okay. So this is a measurement of spectral usage by sticking a spectrum analyzer on a roof. The red represents significant energy in that band. So this is bands. This is time. And the green is not enough. So there's a threshold that was used to decide what would be colored green and what would be colored red. And the threshold was set to the threshold that is used for avoidance of military radars in the 5 gigahertz band. So what if you were to do that same strategy of detection in the 0 to 2.5? But we'll soon come back to why this is kind of fishy. Right? So yeah, this is time, frequency. Yeah. So it's just a measurement that says most of the time, in most frequencies, there doesn't appear to be much. But what is much? That's going to be one of the core questions that this talk's going to try to address. What does it mean for there to be something there? So people think that this is a problem and what to do about it. Now, sometimes when you talk to the economists, their answer is, well, the reason there's a problem here is that somehow the government's actually a bunch of communists. And they have this central planning board which decides who's going to use what band, and we all know communists are inefficient. So that's one sort of caricature of an answer. Now, what to do about this? Well, one is to say, well, the current system is entirely broken. Let's eliminate this idea of having these legacy users in particular bands, and let's move to a comprehensive commons where people use spectrum etiquettes to share, and they point to the success of the Wi-Fi band as the reason one should do this. So that's one approach. I'm not going to talk about this approach for one very good reason. And that's, if there's no scarcity, why should we have to throw away billions of dollars of investment that's already been done in wireless technologies? So let's think about what it would take to preserve some sort of priority for primary users. These are all the legacy systems that are out there today. Cellular, TV, and so on. And so how to think about the different possibilities here? So the way that we think about the different possibilities is to say, well, whose responsibility is it to manage interference to the primaries? One choice is it's the primary's responsibility to manage his own interference. The other case is it's somebody else's responsibility. And the other case is for the secondary who wants to use the band, does it require permission, or must it somehow, in some sense, be careful? So when it has permission, it says, okay, I know I have permission, so I can feel free to use it. I don't have to be careful anymore. So in this corner here, where it's the primary's responsibility and the secondary has to have permission, well, then the secondary has to have permission of the primary. In that case, this has the standard markets idea, that you say the primaries own their bands. If someone else wants to use them, they have to ask for permission, and they'll presumably have to pay to get permission. And then the question is, how does one structure a secondary market, and so on. Lots of questions there. Now, there's another flip side of this. You could say that it's the primary's responsibility, but the secondary doesn't have to have permission. What would that mean? That means the secondary operates under the principle that at some level, silence implies consent. So if it starts using the band and nobody objects, it's fine. So there the idea is it's the primary's responsibility to send a denial signal to the secondary and to say, hey, you're not allowed to use this band. And then the idea is, again, there could be a market there where the primary issues a denial and the secondary says, oh, well, hold on, don't deny me, please. I'll pay you so much if you let me go. Right? There's another. Now, for some reason, this gets a lot more attention than this, and I don't really know why. It seems to be sort of symmetric. The other case is that interference is not the primary's responsibility to manage. The primary expects to have no interference because that's how its system was built and doesn't want to change its systems. Well, in that case, one way to get permission is to say the UWB approach, where the FCC just says, speak very softly and use a very wide band. And if you do this, you're not going to cause interference to the primaries. And the FCC sort of sets these levels. Now, this is a spectrum sharing regime because the reason it works in terms of getting high data rates in the bands that it's using, 3 to 10 gigahertz, let's say, is because there's very little usage in those bands. So the system, it's true, the UWB system operating might not cause interference to a primary system in those bands, but the reason it gets a high data rate and can be built in a simple way is that it doesn't have to worry about rejecting interference from primaries in those bands because they just aren't there usually. So it is also a spectrum sharing approach. This talk focuses on the final corner, the opportunistic or standard cognitive radio approach, where we say that the secondary has to be careful, and so it's the secondary's job to manage interference, to make sure that the way it's being careful, it will not cause too much interference to the primaries. And that's the focus of this talk.
How do you define the primary and secondary? Is there a precise definition?
Yeah, primary is the person who has a license to the band. So it means, for example, a TV station. That's an example of a primary. A secondary is somebody else who wants to use the band. So for example, you would like to set up a Wi-Fi network over TV band. That's what I mean by primary and secondary.
When you say somebody else's responsibility, what do you mean by that? That could be somebody who's in charge, like a police officer?
Yeah, of course, all other possibilities here as well. It could be that there's someone else who's the police who maintains that, they make sure there's no interference, and yeah. So this is just the 4 possibilities here. There are others that fall into these categories. These are representative samples here. So for the police, the question is how do the police decide whether someone's causing interference or not? In what sense should the secondary have to be careful? So for example, it has to listen for the police to tell it things.
Like a radar detector.
Yeah, except the other way. More like not putting its headphones on while driving so you can hear the sirens.
So the
Yeah.
ISM band, who is primary and who is secondary?
The ISM band, there is no primary. Instead, everyone's has a blanket permission, the Part 15 rules. So it's kind of a limited version of UWB. You're given blanket permission in the band. There's no primary. I think, there technically are some primaries around, but I'm not sure. I don't know the exact detail. But pretty much it's a UWB style. You're given Part 15 rules, operate within them, and you're considered to be okay. If someone is bothered, well, it's not your problem. They shouldn't be bothered by you. Of course, many ISM band users think of themselves as primary. So one sees cases like what's going on at Logan Airport, where Logan Airport says, I'm primary. This is my airport. This is my wireless network. And I don't want you to set up your United or someone. I don't want Continental. I don't want you to set up your own wireless network in my airport. But that's a separate issue. That's not at the FCC or technical level. So before I go on and talk about what are the limits for opportunistic use, I think we should step back and ask, why is it that we have this current situation? Are the economists right, and it's because there's something communist going on, and communists are inefficient? Is there a technical reason that we have this existing waste? So it's always important, because if you say you're going to a new solution, you have to ask, what's the problem that the new solution is solving? That you presumably should solve the same problems the old solution was solving. Right? That's the first principle one has to understand. So the way we think about it is we say there's basically 3 R's that you want communication systems to satisfy. You want them to have good rate, good reliability, and good robustness. So when we usually think in terms of communications engineering, we tend to focus on rate and reliability. So we say we want to fight the ergodic uncertainty in a system. This is the noise. And the way we do that is we compute Shannon capacity limits, and we think about error correcting codes that try to approach those limits. But in reality, all engineering is about adding redundancy to systems in the right way. Theory is meant to guide you and tell you where you should be putting in redundancy and where you don't need to put any more because you have enough. Because you want to make them also robust. So they should work even in the face of other stuff. So in cellular systems, we often think about the notion of outage. So this is the non-ergodic uncertainty of fading. Sometimes fading comes, and you can't hope to average over it. So you have to be robust to enough fades. So you build a fading margin into your system. But there's also other aspects of robustness that when you think about wireless systems as a whole, coexistence with others means that your system should work even though other systems are operating perhaps not in a 100% modeled way. So there's always a trade-off. You want to model the rest of the world to the level that you need to, but not so much that the other side becomes frozen and can't move. So this is an engineering principle one has to think about. And now the traditional approach, the static allocation, it tried to assure the second kind of robustness, this coexistence with others robustness. And it did it by saying, you sit in your frequency band. We're going to take advantage of the fact that LTI systems have the sinusoids as their natural eigenfunctions to say, as long as you transmit in your band and you're not moving around at ridiculously high speeds, you're not going to enter into the neighboring bands too much. But we know that things are not going to be 100% restricted to single band. So we have these guard bands. So we say that between one frequency allocation and the next frequency allocation, there's going to be a gap. So that whatever you're doing inside your band, as long as you maintain to your transmit power constraint, will be attenuated by enough to the next band, so the next band doesn't have to model you very precisely. And the same kind of guard bands are done in space, where you say, okay, this is your service area for this TV station. I'm going to have another TV station spatially separated away, and it's not going to, I'm just going to put the regions of service right next to each other. I'm going to leave a big gap in between so that the signal will attenuate enough across space so that by the time it enters the other guy, they can ignore it or model it very little, whether you're there or not there. So this is the idea of robustness. Now, that's giving rise to these frequency plans. Now, what we have to do is we have to ask, what's the timescales here? So let's think about the timescale frequency planning. It seems to be years to decades. This is the timescale at which you go to the FCC, say, I would like to have this new service. They approve it. They then decide which bands are good for it, and maybe some international treaties are negotiated. And this sort of happens on this very long timescale. Think about the corresponding spatial scales. The spatial scales involved for the FCC licenses, they don't say, you have a license to use this service in this building. They don't tend to operate at that granularity. They say, look, this is the cellular band, and it's allocated to Verizon for New Jersey, or maybe not even New Jersey, the Northeast. These big swaths of region. Sometimes maritime radar, globally, international treaty. So that's the spatial scale. Now, what's the scale at which the actual use happens, the use that's being protected, who you want to guarantee robustness? Well, that depends on the application. Some applications have very long time scales and very long spatial scales, but other applications, let's say downloading a song from a website, it's on the milliseconds, minutes time scale, and the spatial scale is a few meters from you to the access point. So it's this vast gulf between these spatial and time scales. So you want to have robustness, but the robustness being guaranteed at this scale, while you want it at this scale. So of course you're going to be conservative. It's natural. So it's not like this waste is just there because somehow the FCC is doing a really shoddy job and they're just all want bribes or something. That's not what's going on. They're really trying, but they're limited to operate in this way. So whatever else we talk about, we have to see if we can't preserve some sense of robustness and have an analysis of how to do it. And that's what essentially this talk is about. So a picture of this might be, so if you want to have a model in your mind, it's think of a vase, and that's the spectrum. And you want to fill the vase with usage. But you can only throw in boulders. It's a giant vase, or rocks. After you've filled it up with rocks, it's still going to have lots of room for sand, or water, or pebbles, or anything else. And unless the rocks are completely cut so they just perfectly fit, but that's not reality, right? And that's essentially what's happening here, sort of intuitively. So our objective in opportunistic use is to somehow get some pebbles and sand into that vase. We want to reclaim underutilized spectrum for new uses. We want to have this peaceful coexistence with primaries. So we don't want to mess up their robustness. And we would like to do it, hopefully, with cheap and possibly simple devices. And so what we have to understand is, what is the trade-off here? How cheap, how simple can you make things and still have them work? So how does one begin to formulate those problems? So the core question is, if a radio system transmits in a band and nobody is listening, does it cause interference? And the answer is no. It's not some riddle. And so this is a historic slide for me, because I first gave this talk at Allerton, which is in the middle of nowhere in Illinois. And the idea was, if you're set up a transmitter that starts using a band in the middle of nowhere and you send some signals, is anybody going to mind? The corn's not going to mind. No one's going to mind. It's not like you're going to exploit the land and somehow it'll become less useful in the future. Once your signal is gone, a few microseconds later, it's back to its original shape. So now, of course, this is not going to be interesting from a commercial perspective if it's only about the cornfields in the middle of nowhere. And thankfully, those measurements were done in Berkeley, which is a pretty high-tech place in a pretty high-tech region. And still, there's lots of seeming empty space. So the objective is, we want to move from essentially open loop guarantees of robustness to closed loop guarantees of robustness, where the idea is, rather than saying in advance we know we're going to be safe because the system was built safe at design time without any kind of measurements of the environment, we were instead going to sense the spectrum and then communicate over it. Yeah?
Why can't the FCC trade on the final granularity in terms of time and space scale?
That's an excellent question, right? So there's lots of reasons. There's some history involved. One is simply a matter of administrative cost. One has to think about this. How do you manage that cost? So are you going to put a UAV, with a supercomputer in it and a wideband cryogenically cooled sensor array that flies around a locality, and you communicate to it? Say, UAV, I'd like to use the band. UAV says, yes, I will. Here's your band. That's a possibility. There's some cost associated with it, and one has to figure out what will it take to move that regulatory authority in the right way. Could be say, well, maybe I can delegate some of it to maybe users by themselves. Be nice. Don't muck around too much. And that's essentially what the opportunistic idea is. You kind of delegate to the users and say, look, you have to take care of this yourself, and you have to somehow show that your protocols are going to be safe. Now, but the question here is always about evaluating. You need to have a model so you can then evaluate the trade-offs here. And so I think right now the question is open. Is this flying UAV the right approach? Right? Is it delegating it out to municipalities? No one knows. Historically, so I actually asked some guy at the FCC when they came to visit us at Berkeley, why don't you let the municipalities take over spectrum management? And his answer was never. Right? And it wasn't just a never because that's taking power away from my central authority. There might be a little bit of that, but that's not the main reason. The real reason they're concerned about is some kind of services naturally deploy on these larger scales. And they're thinking, well, right now, their view of hardware is that hardware needs to have a market of millions of units to amortize the cost. And you want to make sure that you can sell to a global or at least a national market. And so you want to make sure the rules are uniform over that market. What's thinking about all of these approaches is that one feels that the hardware is going to change, that frequency agility is going to become a part of hardware in the future. And once one has frequency agile, then one can think about moving away from this scale. Right? And also, in the initial model, the time scale of regulation was that of many generations of device lifetime. So you could iterate a couple of generations while having your rules fixed and sort of know what to expect, rather than having everything change all the time. So it's also the model of how one does certification. You certify devices at building time. So we want to say, what will it take to move to this newer, more dynamic world? And the outline of the talk, which I think, depending on my speed, I'll cover parts of, is first I'm going to walk you through the very basic issues to understand what does it mean for a band to be empty at a very basic level when one doesn't have to worry about robustness questions first. Then we're going to take a look at robustness issues. We're going to start pointing them out here, and then we're going to look at them on the signal processing side for sensitivity to say that you can't actually make things work to arbitrary precision, and there's reasons for it. Then I'm going to talk about ways to give robustness in the face of these problems, and I'll talk about two different kinds of cooperation. One is cooperation within a single system, and the other is cooperation among systems. The main consideration within a system is going to be robustness, in particular to fading, and the main issue in cooperation among systems is going to be some sense of fairness. And then I'll close with some speculations at the end. In a sense, what this is going to be building towards is to say there's basically, at some intuitive level, a conservation of complexity principle here. That you can make your system maintain a particular level of robustness, and you can pay for it in different ways, but you have to pay for it. So for example, you can use much more complicated signal processing algorithms, and that will let you, for example, reduce your cooperation among systems. Or you could have much more cooperation among systems, but you have to pay somewhere. It's not like you can have everything for free. So one of the conclusions is going to be no $10 YCOG cards in the foreseeable future. So for people familiar with classical communication, it's good to show the key difference. Classical communication is focused on, can I decode the data that at the appropriate range and using a reasonable amount of transmit power. So you have coding gains bounded by channel capacity. You can have fading margins built in. And then at the end of the day, you want to know, what's my link budget? So how much transmit power do I need? And the important thing to realize is the typical case. Most of the time, you have more than enough SNR to work in. You built in a fading margin in there to give yourself a little bit extra so you can push it into some of those more of the fades. But typically, you've got more than enough to do the job. Our new constraint in opportunistic use is we must not interfere with the primary users. The idea is we don't want to mess around with them. So we're going to think we have some allowable probability of harmful interference, which the DICE-BAN conference sort of revealed in one of the discussions is probably something around 1%. There's apparently some court case to this effect, 1 to 2%. And the question now becomes, the idea is we want the secondaries to be careful on their own. So they have to sense the spectrum. And the question is, how well must they sense the spectrum in order to guarantee that the primaries are not going to be interfered with, at greater than 1%?
1% over time or over space? Or?
Yeah, it's kind of unclear what 1% here means. So I'm going to think of it as 1% for a communication instance, or for the decision of making whether I should communicate. And I'm going to think of it, instead of 1% of receivers, I'm going to think that there's some receivers which we're going to write off. So we're not going to try to be every receiver is fairly going to be interfered with. Some receivers are just going to get the shaft. I mean, they're not going to get protection. But other receivers are going to be protected, and I want all the protected ones to have only a 99% guarantee that they're not going to be interfered with at the time scale that the secondaries decide I'm going to use the band. That's roughly the model I'm going with.
One thing that is classifies as misdetection probability.
Well, it's almost misdetection probability, but there's a little bit extra you need. So this certainly bounds misdetection probability, but misdetection probability might not be able to be made that low. Now, the main problem here is that the typical case is that you want to use the band. And we just said most bands are empty. So the typical case is the primary signal is not there, or it's very weak, which is to say it's a very low SNR situation. So all kinds of new considerations are going to come in from having to be careful in very low SNR situations. And but thankfully, there's a cause for hope, which is that we don't need to decode the primary signal. We just have to detect that he's there. And he's there at a strong enough level. Once we know that, we don't care what he's saying, because we're not going to use the band. We're not interested in eavesdropping on him, just in figuring out whether he's there or not. So now comes the question. what does it mean for a band to be unused? So I've taken the same measurements from before, and instead of plotting them time versus frequency on a threshold, I've just looked at a particular time instance, looked at frequency. So my laser pointer is dying here, I think. Yeah, frequency, and some measure of the level. Now don't worry about the units here. I think the old threshold was drawn somewhere around here. And you see that, well, is this nothing or is this something? Is this something? Is this a something? So is it safe to use this band or not? Right? Over here, yeah, maybe it's safe. Right? But what about over here? What's the level that constitutes nothing? Now, this is not to say, can I get good data rate if I use this band? Oh yeah, sure. Go ahead, use the band, you'll get great data rate. This is not going to interfere with your communication. The question is whether you're going to interfere with them. So it kind of depends on what they are and what you are. And that's the next part. So I'm going to focus throughout on the typical picture. The model picture is that of a television. Just because in some sense, which will become clear, television is sort of the easiest case.
So,
Yeah.
in the previous slide.
Yeah.
So is your highest value minus 100 dBm? That's like usually below noise, isn't it?
Yeah, so that's what I'm saying. The student who made this plot, I'm not sure, is like amplitude, it's not like energy, and there's something else. These units are kind of fishy here, right? So don't worry about the units.
dBm, I'm saying sort of typically when they talk about just noise, right? You just look at the noise.
Yeah.
It's like at about minus 90 dBm, I think.
No, it's like minus 106 or
Minus
106,
or
yeah.
something.
Yeah, but this is clearly, this is not. Don't look at the scale. The idea is this is what it looks like qualitatively, and there's like strong TV signal, cellular, and so on around here, right? They're all in here. But yeah.
It's not an amplitude.
Yeah, I'm not sure. I have to ask them what they did exactly. This is a BWRC measurement that Daniela and Bob did. And okay, anyway, so the important thing is that is not is a question: where does one draw the threshold, and what does that depend on? So we think about a TV station in a magical, ideal world where everyone lives on a flat plane and there's no fading. So here's a TV tower. Here's everyone who can decode the TV signal. Beyond that, there's too much attenuation from distance, and you can't decode the TV signal anymore. So think of HDTV. What we're going to say is the users inside the green are the ones we're going to protect. So when opportunistic users come into town, these blue guys, they might lose service. And the idea is these guys in the blue, they're pretty much near the edge anyway. So for example, if a truck drove by in the wrong way, the guy at the very edge would lose service because he's going to get a little bit of additional fade and push him below. So we give up on them, and we say, but everyone in the green, we want to give them that 1% guarantee, that they're only going to be interfered with 1%. So now, we'll take the perspective of user at B, and we're going to say, I'm a secondary user. I'm the only secondary user in the situation, in the entire world, and I'm going to start transmitting. How far away from you would you like me to be? So he says, well, if you're a mouse and you squeak, send out a very weak signal, I'd like you to be this far away. Because if you're closer than that, even your little mouse squeaking will be too much for my system. But when you're beyond that radius, fine, you'll be attenuated enough by the time you come to me, and it won't bother me. So if we were a mouse system, we just have to detect whether we're out here or not. But if we were a lion system, and we roared, transmitted larger power, he would say, you stay further away from me, because I need you to be attenuated enough by the time you come to me that you don't knock me out of service. So he's going to say, lions have to stay far out. So now for a lion system, for a band to be unused, means that you can show that you're out here. Versus for a mouse system, you only have to be out here. So we see here that what you need for a band to be empty depends on who you are, and what you want to do, and what the primary is. So one can make this kind of a plot and say, okay, let me look at how much more sensitive my secondary receiver is than the primary. And then we look on this axis of how much power I'm allowed to put out as a secondary system. So the more sensitive I am, and I can verify that I am that the primary is below that sensitivity, then I know that I'm very far away, and so I can put out more power. So now let's think about what the primary is. Here, I'm saying the primary is actually those pebbles filling the vase. So these are little 802.11 transmitters filling, sitting somewhere. And we want to be a secondary user and use the band when the 802.11 is not using it. So then, well, there's very little power we can put out, and we have to be very sensitive to get more power. The reason is that it's like that picture where you have the signal's attenuating with distance, but it's attenuating with distance as 1 over d to some power. That's the model I'm using. So being far away in attenuation doesn't mean you're far away in space. Because think about a 1 over d curve, right? It looks like this. So the initial part has a much steeper slope than the further part. So over here is the same thing done for a digital TV transmission. So here you can put out a whole bunch of power if you're more sensitive. Because if you're more sensitive, and you're more sensitive than the guy at the edge of the protected radius, the decodable radius, it means you're really, really far away. So, because the decodable radius is already at 51 kilometers away here, so to be 10 dB more sensitive, you're talking about being many, many kilometers away. So you can put out a lot more power without bothering anybody. So this validates our picture of this vase filled with pebbles or rocks. If it's filled with pebbles, there's going to be room for smaller particles than if it's filled with rocks. You can put bigger things in. So that's how one can do these calculations. And of course, it varies on the relative attenuations, and that's what the other lines are for. Okay, so far we've lived in this ideal world which doesn't have fading. But in real life, there is fading. So what are we going to do about it? So the basic question is, if you're the red user or you're the blue user, now think of yourself as a secondary user, and you're listening for the primary signal, you're going to hear the same level of primary signal. Here you're behind a building, here you have a clear view. So if you're trying to make your decision on whether you can transmit or not based on what you're hearing, well, out here you'd be safe. Feel free to transmit. You won't bother anybody. But over here, if you transmitted, you might knock people out here out of service for the primary. So that's not safe. So what's the first thought you have as an engineer? You say, OK, let me pick a fading margin to account for this. And I'm going to say, OK, too bad. This guy is going to lose the ability to communicate because he can't be sure. But at least for that vast amount of spatial area which is out there in the open, we're going to get that. So the question is, how do you choose the fading margin? So fading margin just shifts everything over by that many dB of sensitivity. But how do you choose it? Is 10 dB a good number? 5 dB? There's got to be some principled way of choosing this.
I think I missed something about this slide.
OK.
So what is the x-axis of these curves?
Oh, the x-axis is how sensitive we are. How much more sensitive the secondary is than the primary's decodable radius. The primary at the edge of decodability. So the primary needs a particular SNR to be able to decode.
Right.
So we say
It means around the primary there was that circle.
Yeah.
To have him be
the blue circle. Yeah.
Depending on how powerful he is.
Yeah.
Okay.
So we're saying how much more sensitive are we as a secondary than the primary in being able to detect the primary is there or not there. So if we can rule out that so it's basically about saying how far out are we here that we can assert that, okay, based on my measurements, I didn't hear anything. And because I didn't hear anything, it means I'm at least this far out. I might be this far out, but I'm at least this far out.
So how do you, the thing you're trying to be far away from is television, right?
Yes, it's always like television. Yeah.
That's a TV receiver.
TV transmitter. You're trying to be away from the TV transmitter.
Who cares about whether you're near?
Yes, of course. There's a slide that's like 2 slides down which says exactly that. But yeah, so here we're saying if all you can do is measure, and you don't necessarily know where the receivers are, then you have to be conservative. And you have to say, well, I don't know where the receivers are, so I'm going to assume that if I can decode TV, there's a TV receiver nearby who's also decoding TV. Of course, there might not be one, but unfortunately, it's all the information I have to work with. So I have to be conservative robustly over all possible TV placements. Because I don't have a PDF for TV placements. Because I don't even know where I am. So because of this, of course, I could model where all the receivers are. That's more modeling complexity, and I'd gain something for it. But so one wants to see how that trades off.
You have higher recurrence and sensitivity of your front end.
Yes. So, but remember, it's a simpler question. When I talk about sensitivity in terms of, say, present or not present, not to decode. So you might not be able to decode him, but you can say, is he there or not?
So if you can somehow, if you say, oh, I'm in a place where the TV signal is decodable,
Yeah.
then you don't transmit.
Then you don't transmit. Because you say, TV signal's decodable, there's probably TV nearby. If I transmit it, he's right next to me, he's going to lose service, so I can't do it. But you say, I'm in a place where the TV signal is not visible, and it's even if it was 15 dB louder, it's still not visible, it still wouldn't be decodable. Then I'm pretty sure that I'm far away from TVs. And I say, okay, maybe I'm faded, but even if I'm faded, I'm far away. Right? So if I were to communicate, feel free to transmit at this much power. And I won't bother anybody, provably.
Okay, now
So fading just says, be more sensitive. Now the question is, how sensitive? How much fading do you account for? Now, I can tell you by talking to people in the 802.22 working group, the way they're answering this question is politics. They sit around a table and say, how sensitive can you be? How sensitive do you need me to be? Maybe we can work something out. Okay, this is good. Right? That's not good engineering. Right? Good engineering is we need some principled way of saying, how do you choose the fading margin?
So
Yeah.
in your case, you actually didn't consider who I will transmit to the secondary.
Yeah.
Actually, if I only if receives very small downlink to transmit a very small power, even I'm in the middle.
Yeah, so that's what this trade-off is. This is like saying, how much power can I use based on how sensitive I am? How much you need, that's a separate question. It depends on how long you want to, how low a data rate you're willing to live with, and all kinds of things. But this is only asking the question of getting access to a band. What you do with it, separate question.
Okay. I just feel like your expense depends on how much you need it.
Well, presumably. But this is like the question before that. So you want to say, one of the things is, how much is there? How much do I need? So this is like the how much is there question that comes before the how much do I need.
So what is the time scale in the secondary operator? Suppose
Yeah, there's all kinds of temporal questions. I'm going to mention them in a bit. But right now, think of it as TV's either there or not there on a time scale of years. And we're going to sense on the time scale of hours. So we're well within the primary's time scale. So we don't worry about it. Of course, it is a natural question. So here, the principled way of choosing fading is to realize that your probability of misdetection that you can live with is the probability of having a good fade times the probability of missing a good signal. Now this is something near 1, and this is missing a good signal. This is presumably small. Plus the probability of a bad fade. Because in a bad fade, you have no hope of seeing the signal. So what this says is all the terms here are positive. It says that your probability of bad fade can never be larger than your probability of misdetection. So if you want to have a probability of misdetection below 1%, it means that you must account for, you can't just write off a 5% fade as a bad fade. You can only write off 1% fades as bad fades. So you could conceivably say, okay, what's my model for fading? And say, okay, look in the literature. It's log normal for shadowing, Rayleigh for the multipath, pick values, and look up, okay, how bad is a 10% fade? Oh, it's 16 dB bad. How bad is a 1% fade? 21 dB. How bad is a 0.1% fade? 26 dB. Okay, so 26 dB is my fading margin. Right? One could do this, and it sounds legitimate, except for anyone who's been out there actually designing wireless systems, who says, this is all crazy. Because all these deep fade probabilities, they're just made up. They're extrapolated. They're not well modeled. The Rayleigh stuff, sure, that's sort of well modeled. But this log normal, this is averaged over environments. And any deployments in a particular environment, not averaged over environments. So you can't say that your system is built robustly because you allocated a 26 dB fading margin. Sure, it's sort of robust, but how robust? What's the relationship to probability of harmful interference? You don't know. In general, you don't want to engineer systems that depend on modeling very rare events. of course, you could have some calibration stage where you sit there, send out, and figure out a way of calibrating your shadowing model. But that's more complexity. So this is one of the uncertainties we're going to have to deal with.
So how often are you sensing and how long are you sensing?
Yeah, good question. How long we're going to sense is how long we need to, and how often is the next slide.
Yeah, the reason is because, maybe this is what you're going to say. Why should you even bother with the log normal?
Oh, because if you're shadowed, right, you're shadowed to the primary, but not to the other receiver. So think about, I'm behind a building, and behind me is another building where someone's watching TV. So I can't get TV reception at all, so I'm assuming a log normal shadowing through the building. And the guy behind me, though, if I were to start transmitting, he would lose service. So I have to account for shadowing. That's why. That's the reason for thinking about shadowing. Or think of some other model for shadowing. If anyone's got a reliable, robust model for shadowing that they have confidence in and are willing to bet their 1% life on, tell me. I have not seen these things.
So what kind I walked in on your slide 7.
Mm-hmm.
So the secondary users, what are they going to be doing?
Talking to each other.
Moving around there.
Yeah, they're moving around, talking to each other. They have some need to use the spectrum at some particular level of power. That's all my model is right now. So, for example, they might be Wi-Fi type systems. So they would like to establish a Wi-Fi type network, but they don't want to use the ISM band. They want to use a TV band to do it. That's a model of what it is.
Because if you assume that your log normal is sort of relatively unchanged, right?
Mm-hmm.
Sort of when you're doing your sensing and wherever you want to do your
Yeah.
communication. It seems like the replicating is a pretty good model, and you can get a reasonably good.
Relay is fine, but the log normal is the problem. So you sit there, someone buys a device. This is the YCOG access point. Sticks it in the building, plugs it in. Now the YCOG access point has to pick a band. It's going to be cognitive. It's going to search around, look for a band, and work. The YCOG access point, it doesn't have... So one thing is, of course, it quickly deploys a little drone, like in the movies, right, that flies around, right, figures out where am I, what's the shadowing environment, is there a TV station, right, and the drone flies back in, and then it picks a band. Of course, this is like the $10 million YCOG access point. That's not reasonable. So one says, how much could it do if it just sat there, in the room, sensed, and picked a band? Well, then it might be shadowed, and it doesn't know how it's shadowed. So it has to account for some margin for shadowing. That's what I'm saying. That you can't really do that in a reasonable way if you want this 1% kind of reliability, because you don't have a model for 1% things. Plus, you're going to have this huge fading margin. So most of the time, 95% of the time, you're not going to face this kind of crazy fade. But you're going to think, maybe I am, so I can't use the band. So it's conservatism. And it's also bad conservatism, because it's not robust to what you want to achieve. So let's see, what's my time? Oops. Okay, so I'm going at 1/4 my speed. So there's similar things for temporal. People ask how temporal gaps will do this, and I'll just maybe stop, go to the end or something. So there's temporal gaps. And we're thinking here the temporal gaps of the primary. Because we said that TV is not so much. TV is on, it's on. But other primaries, one could imagine, have on and off cycles. They have different kinds of cycles. So for example, think of a Wi-Fi type of system where you have different levels. You have whether the link is active in the sense that someone has a session. So someone clicks and says, I'm now doing instant messaging. And they're in an instant messaging session. And they also have level at the level of the actual packets. So it's activity at the level of packets. So one is you want to recover the gaps between packets. So here, what you want to do is you hope that you can robustly detect the activity within a single on period when it kicks on, the packet length. And the key issue here that needs to be addressed is what's the non-usage coherence time? So what do I mean by this? I mean that suppose you think that someone's doing instant messaging. You sense, and he's not there. So what? Right? Does that mean he's not there for the next second, the next millisecond, the next microsecond? How long can you trust your he's not there measurement? And that's an important issue you need to think about. And this needs to be modeled and someone needs to figure out what to do about this, right? I think basically it's a modeling question.
Is it a modeling question, or is it a question of just designing an appropriate measurement system?
No, suppose I have a perfect measurement. I have an ESP measuring system, right? It can't look in the future though, right? And it just says, the packet is being sent, or no, there's no packet being sent. Okay, now based on that, what's the conditional probability that in the next microsecond a packet will be sent and you will cause interference? Or what's the model of causing interference? So I think the current way people think about it is that maybe it's okay for these packet type systems. If you bother them for a little bit, it's okay. So you say that, I'm allowed to bother it for like a millisecond because it'll just do a retransmission and then I'll back off by that point. And I'm really trying to get the other kind. I'm really trying to see, actually he's not instant messaging at all, or he's not doing a download at all. He's just idle.
So then how about sensing continuously, like even if secondary is transmitting?
Sure.
Decide that it's going to transmit.
Yeah, sure. Sense still. Problem is causality. You can't make decisions in the past. You have to make decisions in the future. So you have to use the past to figure out what's going to happen in the future so you can act. And that's the problem. So one can imagine, and it's an exercise for someone, figure out, suppose you model the usage pattern as being on-off two-state Markov chain in a Markov process with exponential transitions, the usual kind of transitions one models. And now look at the conditional probability. It's easy to see that in many cases, if you, based on your target probability, it's this memoryless process, right? So he's not transmitted, but he might transmit the next instant. He still hasn't transmitted. He still might transmit the next instant. And you have complete denial on the band, to be conservative. So how do you model it, right? What's the right model? What's the right engineering thing to actually have robust non-interference? This is an open question that needs to be worked out. Now, there's another thing. You could say that maybe I'll sense continuously. I'm not going to try to exploit the inter-packet gaps. I'm just going to try to exploit the inter-session gaps. So then you can say, okay, there's 3 or 4 different Markov chains. I don't know which one it is. I'm going to try to figure, and one of them is, of course, no activity forever. I'm going to try to robustly rule out the ones that are activity I might bother and figure out that I'm in the activity that I'm not going to bother. And again, one has this case. If you can robustly detect within a single period, then you can basically watch the transitions, the packets. And then you can make a hypothesis test based on that. Of course, you might think that maybe the signal is actually very weak, and you can't actually detect a single packet very well. So what you want to do is say, look, if it's actually a file transfer that's going on, I don't have to catch every packet. I can listen for actually, say, 1/10 of a second and average over many packets and still detect. And because all I want to do is to rule out that it's an active period. A session is active or session is not active. So now there's another kind of attenuation that you have to worry about. In a sense, it could be a file transfer, or it could be an instant messaging session, or it could be another kind of a session. And you need to figure out that when you're averaging over the on and off times. So in a sense, your signal is attenuated by the duty cycle. So it's like another kind of fading. And you have to model what's a low probability duty cycle. So how low can the duty cycle be while still being an on session? So unfortunately, there's been some work on this that says those are also very poorly modeled. So for example, Poisson and other models really don't work very well for low probability duty cycles. How low? 1% low. Same as before. So the same kind of problems hit you here. My gut tells me that probably this is not going to work. You're going to have to make sure that you can detect single on periods and then do session figuring out which session you're in or not. So you have to say, I robustly can tell where the packets are. And I just want to figure out, classify the session. So that's all I'm going to say about temporal gaps, because they're even harder. Because the problem is, unlike fading, which is spatially ergodic, one hopes, temporal gaps are not spatially ergodic, because they're time. It's either I'm not using it, and I'm not using it across all space, or I'm not. And there's no way to average over this. Okay, so what this picture gives up is this uncertainty, which is so all this green annulus is a place where you could have communicated secondarily and not hurt anybody, but you unfortunately built your fading margin so big that you're giving it all up. So this is coming from your conservatism, and you're just giving it up in terms of area that you could have reclaimed for your secondary use. We can get some of this back by getting rid of the need to be robust to very, very deep fades, by having something else which lets us maintain that same robustness. Then there's this one. This is the home shopping network at 3 a.m. So the home shopping network is broadcasting at 3 a.m., but only 3 people in the city are listening to it. So you could use the home shopping network bandwidth over here to set up your wireless link, and you wouldn't bother anybody, but you're not modeling where the receivers are, and so you have to give it up. You can get that back if you have some more interaction with the receivers, or you have a good model for where the receivers are. Finally, it could be that you're actually hearing the primary fine, but the nearby receivers are shadowed to you. So the flip side. But you don't know, because you're not interacting with the receiver. The way to get this back is to interact with the receiver, but if you don't, you have to give it up. This is the trade-off. Model more, get something. Model less, give something up. So far I talked about singles, but maybe I'll just, if you have lots of them, you have to have your probability of misdetection brought down, because it's not enough for one secondary to be quiet. All of them have to be quiet so they don't cause interference. Similarly, one has to worry about having lots of secondaries. So far I've been talking about one secondary in the world. No one's going to do this if it's only going to be about one secondary. It's going to be thousands, millions of units, right, for this to make any sense. So here what one does is say that, look, whatever secondary system, now I'm going to model the secondary system a little bit more. I'm going to say that the secondary system, whatever it is going to have some sort of a data MAC protocol associated with it. This is the MAC protocol it has for data transfer. And we're going to say whatever that data MAC protocol is, it's going to enforce some. If I pack in more users in the same space, they're not going to keep putting out more and more power. They're going to saturate out at some particular density of how much power they put out per unit area. And if you model it as density, you can do all the calculations with density. I'll skip this. Okay, so maybe I'll just go through. When should I actually stop? Just so I know.
I'm not sure. Did we start at 11:15 or 20?
I think we started 11:15, right?
Something around 12:15 or 12:20.
Okay. So
I mean, like it's already 12:30 now, but
no.
I don't know what time it is.
It's like 12:05.
Whether you want us to buy it or not.
Sure. That's a good incentive.
If you're interested in lunch, you should definitely stop at 12:30.
Okay, sure.
Because you have to drive.
Okay, sure. So now we're talking now about the signal processing side. So we say that you have to be sensitive to detect the primary and so on. Detect them at very low SNR. The question is, can you do it? If you can't, what's limiting you? What can you do about it? So here the picture is, how well are you going to model the primary? Do you know the primary, and what parts of the primary are important to model, and what parts of the primary are not worth modeling? That's the question that one needs to answer. So suppose you model the primary using the simplest possible model. There's the band of interest. He puts out some signal which is basically unknown, except at the level of knowing what power it is. So you don't care what modulation he's doing. You don't care if there are pilots, no pilots, pseudorandom noise things, training sequences. Forget all that, just some energy. Well, simple model, pretty robust to different variations of the primary, but what does it do to your sensitivity? So the problem here is one can set up an energy detector and write out ROC characteristics. This is an exercise from your basic detection classes. But you always assume the noise is Gaussian. And it's Gaussian with a particular second moment. But are you going to bet your life on it? That it's Gaussian? No, not really. Right? It's sort of Gaussian, maybe. So where's your uncertainty about the noise? Well, there's nonlinearity in the components. There's variation across manufacturing. There's thermal noise which changes through time and it's non-uniform. So that's some kind of uncertainty. But you also have more. In that you put up your antenna, and maybe you can calibrate all this stuff by disconnecting your system from its antenna. But you connect your antenna, and you're not just picking up the primary. You're picking up unintentional emitters nearby, things like laptops, washing machines, vacuum cleaners, the stuff in the environment. Are you going to model that? Intentional emitters far away. There may or may not be another TV station many, many miles away. Opportunistic users like you, who have also decided this band is empty and start using it. All these are going to contribute signal into the band. So what does that mean for your noise? All this you consider noise because it's not primary. So you can think of it like this. You have some nominal noise PDF, but you have an uncertainty set also. So you say that, well, it's not just the nominal noise PDF. There's going to be other stuff in the neighborhood of the nominal noise PDF that's also potentially there. And your detector has to work robustly over the entire uncertainty set, not just over the nominal model. So the problem is that your nominal noise PDF plus signal might actually be inside your uncertainty class. And in fact, when the signal is sufficiently weak, that always happens. Because the signal sufficiently weak is like a little perturbation in a particular direction. And if your ball has some sort of uniformity, some all axes covered, then a little perturbation in that direction is also going to stay inside the ball. And so one's going to get fundamental limits on sensitivity this way. So thought about in terms of the energy detector, just project everything into energy. You see that the test statistic is energy. High enough energy, you can say, yeah, my noise uncertainty is only here. If I'm seeing anything up here, primary is around too. But when you see anything within this set, you can't tell. You could say, well, it could be that the primary is around at this level, and my noise at the bottom end of my limit. It could be that my noise is just at the high end of my limit, and there's no primary. Inconclusive. I cannot tell anything. All I can say is that whatever primary there is, he's certainly not this high. Right? That's all you can say. So if you translate this into a curve of where this SNR wall is, the wall meaning that's the lowest possible SNR you can see. I call it a wall rather than a floor because on different plots it looks like a wall. But you can see if you have 1 dB of uncertainty in your noise, which is pretty good. I mean, you probably have more than that. You cannot see more than 3 dB below the noise floor. You can't see it anymore. Now, it turns out that this is I did for the energy detector. It turns out certain kinds of knowledge of the signal are useless. In particular, if I told you it was a BPSK signal, if you knew its modulation was BPSK, useless. It doesn't buy you a thing in terms of where this floor shows up. I mean, it buys you a tiny bit, but qualitatively nothing. And in general, the only thing that'll help you escape this wall is knowledge about some deterministic feature, periodic deterministic feature of the signal that you can somehow average over, something coherent. Otherwise, you just have to live with it. That's the sensitivity. Too bad. So for TV bands, if you have digital receiver sensitivities at minus 85 dBm, thermal noise at minus 106, and if you have rare fading margin such that you have to detect at minus 117 dBm, too bad. You're dead. Right? Your requirements on your receiver specs, impossible to meet. So what are you going to do? So one choice at the signal processing level is to say, let me model the primary a little bit more. In particular, let me model a coherent feature of the signal. It's like a pilot tone. So if I have a pilot tone, what can I do? I can set it up like a hypothesis test and say I have 2 hypotheses. Noise, or noise plus unknown energy signal plus some fraction of energy in a pilot. And you can say, well, I want to fight that uncertainty wall, so I'm going to try to look for the pilot. And the way I'll look for the pilot is to do coherent processing. I'll average against the pilot. And now what happens here is that when one averages against the pilot, as time gets longer and longer, the uncertainty ball sort of stays where it is, but your pilot feature is growing in one direction. So it'll puncture the ball and go out, so you can robustly detect it. Because you assume that there's no uncertainty that might be pushing out in a given direction. Now for a sinusoid, that's probably a bad idea. Right? Because in real life, if you listen for the noise, you will see the noise contains sinusoids. and their sinusoids show up in weird places, unmodeled way. So, but if it's not a sinusoid, if instead it's something like a training sequence, then unless you're worried about other training sequences that are exactly the same showing up, it's more reliable to think that the noise is not going to imitate that particular training sequence. Performance, skip that. But there's more you get. If you think of the dominant term in your uncertainty as being interference from other users, which may or may not be in the band, you get something else. You get the ability to estimate the interference. So the idea here is not so much to estimate the interference at the realization level. It's in estimating the interference at the model level, so you know what its density is going to be, not necessarily what its realization is. We're not talking about filtering it out. We're talking about estimating its level. So what happens is, if you think about, here's the pilot tone, you can measure out here somewhere, and then to predict, based on what you measured, as to what the noise level is going to be at the pilot frequency. And that prediction is going to have some prediction error to it. And what that means is your uncertainty ball is going to shrink from whatever it was originally to your prediction error uncertainty ball. And you're going to get a win here. Yeah.
So in the hypothesis testing that you showed, right?
Yeah.
So is W of n modeled well? When there's nothing out there in the TV band, I mean, suppose there's no TV signal. Is there a good model for W of n?
No. That's what I'm saying. There's a ball around it. It's not, because it's not just, you can't just say there's nothing out there now. The question is, you're going to put out these secondaries. And so what might be out there is other secondaries. They may or may not be present. They may not be talking to you.
Let me rephrase the question. So you're saying there is some nominal around which you can construct an uncertainty class? Is that true? Or are you just modeling it like that?
In the best possible case, that's true. Right? Probably it's not so true in practice. Probably it's even worse in practice. But it might, wherever there is some range of uncertainty that one can model. Or what I'm saying is one has to model. There's no choice. You want to be robust to it. You have to model it at some level. Question is whether you can draw a big ball, whether it's a bunch of little balls. That depends on the details. So at the end of the day, skip all this. Let me go to this point. You still have a limit, though. You're still limited by the coherence time. You can only do the coherent thing as long as you trust that the channel has a coherence time. Now, what's the worst case here? The worst case here is you think the coherence time is 1 millisecond. Or maybe implementation-wise, you can only integrate for 1 millisecond coherently. Beyond that, there's too much complications of doing the frequency binning and so on. You're not willing to pay that much. Suppose you even say, I'm willing to pay, but I think that the coherence time is 1 millisecond. Could be in real life that the coherence time is actually 10 seconds. Is this good or bad? Right? Yeah, it's hard to see, right? Because it actually could be very bad. Because what happens is the coherence time is 10 seconds, which means you don't get a new fresh realization of the fade. You see the same fade over and over again, but you're only doing averaging for a shorter period of time. So you have to live with what you think the coherence time can be in that 1% of cases that you're going to try to be robust in. Anyway, at the end of the day, the coherence time is going to give you a gain, but you're still going to have some residual uncertainty ball that's going to be in all directions that you can never see below. But it gives substantial gains. I'll skip this. Okay, so but it costs complexity. If anyone thinks about implementing a coherent detector, trying to find these things, it costs a lot. So finally, we have this issue of how does one fight it. So the basic way you fight it is to say, cooperate. So this is like the key picture. If you have all these different users, red and black users, if the black users are not shadowed and can say, hey, I see the primary, then all of them can conclude the primary is present. So rather than having every single user by himself have to detect the primary robustly, you could say all of us collectively have to detect the primary robustly. And so now, rather than having to be robust to my own shadowing, I just have to have the ensemble as a whole be robust to the shadowing as a whole. And if I have a good model for the shadowing as a whole on this scale, in particular whether I get independent draws of the shadowing if I'm far enough away, then you don't have to be as sensitive individually. So what does this require? This requires cooperation at some degree of long range. How long? Long enough to give you an independent draw on the shadowing, the part that you have the least model for. Of course, some short range, basically at the level of multipath, is going to help you fight the multipath, but you still need some long range to fight the shadowing. So how far? Far enough to be independent. How close? Close enough to be relevant. I mean, you don't want to have a measurement from a completely different place that has a different spectrum characteristic. So if you do this, the idea is you can now move your probability of detection from 99.99% on the individual radial level to 60% on the individual radial level, which means now you can write off the 40% worst fades. You can say, I don't have to have a good model for them. I'm now robust to how well I model 40% bad fades. And that's going to give you more confidence in the design system. There's limits to this. I'll skip that.
That 60% has something to do with the density of the secondary.
Yeah. It has to do with how many independent draws you get. So here I did 10. So you started with 99.9%, but you got 10 independent draws. That depends on how far your cooperation. This basically depends on your cooperation footprint. What geographical scale are you sampling in? That gives you a footprint of cooperation. That tells you how you can move it. There's limits on this that have to do with another level of modeling, but I don't have time at all to talk about that right now. Finally, this is within a system. You can cooperate with the others within your system. You also want to be robust to whether other secondaries are transmitting or not, that are from other systems. Your system, maybe you can coordinate, but other systems you want to be robust to. So what can you do to reduce your uncertainty? Well, you can enforce a sensing MAC. And what that says is, I'm over here, and I'm trying to sense. I can say, because I'm trying to sense, enforced, even other systems nearby, I tell them, be quiet. I'm sensing. I don't want to hear you. The ones far away, all the way out here, you say, well, they'll be attenuated enough by the time they come to me that I can just model them as an uncertainty ball. Of course, if there's a larger density around me, then I'm going to need a larger ball of exclusion so that my uncertainty ball remains the same at the end. So the reason is I don't know. I say that this is the density, the maximum density that's allowed, but it may be present, it may not be present. The users might be transmitting, they may not be transmitting. I have to be robust to their utilization characteristic at the moment. So what you do is you just evaluate it. There's steps to it, but I'll skip those. So, because this is where the punchline of the talk comes. If you evaluate all this for an energy detector, so we say I want to use a simple detector. How much cooperation do I need? It shows for supporting Wi-Fi type densities in a TV band, it requires an exclusion radius of 5 kilometers. So can you imagine a little Wi-Fi system saying 5 kilometers away, all secondary devices, be quiet, I'm sensing. Well, that's crazy, right? That means it's not going to happen. So that's where I accounted for 25 dB of fading margin because I wasn't doing any cooperation within my system. Suppose I said, okay, I'm going to do cooperation within my system. I'm going to bring that fading margin all the way from 25 down to 10 dB. You can look at that. And it says, for a Wi-Fi system to operate, now it must exclude nearby secondary users that are 700 meters away. Still crazy. So an energy detector-based system cannot robustly function in this way. I mean, the complexity trade-off is too much cooperation between systems. You can't, it's not reasonable. So thankfully, if you switched and you used a coherent detector, so now I model pilots and I assume that there's, let's say, 1% of the signal energy in the pilot, and I do cooperation within my system, so I have only a 10 dB fading margin, then a Wi-Fi type of system operating the TV band only has to exclude users about 35 meters away, which is now reasonable. This is roughly around the range that the data MAC can function in. So I say, look, I'm going to be sensing. I don't care whether you're my system or another system. Be quiet. I'm going to be sensing. Yeah, the coherent detection is good enough. You can have it work. So this tells you you have to pay for the if paying for the complexity in terms of cooperation among different systems is really expensive, then you have to pay for it in signal processing. That's what I meant by this conservation of complexity. You can trade off between these things, but there are limits.
So
Yeah.
your example is the Wi-Fi system operating in the TV band.
Yeah.
And so Wi-Fi is secondary.
Yes, Wi-Fi is secondary.
And the Wi-Fi, so you came up with a number 35 meters.
Yeah.
So what is 35 meters?
This is saying that a Wi-Fi type of what I'm modeling about the Wi-Fi system is not its details of operation.
Yeah.
I'm modeling its essential energy density that it puts out. And I'm saying that the Wi-Fi system says, I'm going to be sensing. So I'm the Wi-Fi access point. I'm going to sense to see if this band is worth using or not. This is a setup time. So I got plugged in, I'm setting myself up. And during this time, I tell other nearby secondary users of this band, be quiet, because I'm trying to sense the primary. And I assume that they obey.
They have to be 35 meters away.
Yeah. So what I do is I say that they're 35 meters away. I tell them, be quiet. And on top of that, I have coherent processing gain of 10 to the fourth. I then estimate the interference. I do interference prediction for all the guys who are farther away to model their interference at the pilot, such that my interference prediction error reduces the uncertainty ball by 1% to only 1% of what it was originally. And at the end of the day, I will be able to successfully detect or reject the hypothesis of the primary being present or absent at the required level of sensitivity.
And you're assuming some transmitted power by the primary
Yes, I assume I know the transmitted power by the primary.
of the pilot.
Of the pilot, yes. And I assume, for this particular case, I said I took the TV signal and I assumed that 1% of the power is in the pilot. Of course, the more power is in the pilot, the better my coherent detector is going to work. So by pilot, I don't necessarily just mean a sinusoid. I mean all the deterministic features of the signal that I can attempt to get coherent processing gain on.
So an access point is just being plugged in, it's looking for
Mhm.
an available band. In practice, it's actually going to experience interference from other secondary users who are already in the band, right?
Yeah, that's what this is saying.
So why does it need to evaluate the presence of just the primary user? Because it has to live with this interference from other secondary users as well if it decides to use that band, right?
Oh yeah, but that's fair, right? See, if so it's like a bunch of it's like a land, right? It's supposed to be used or not used by somebody. If a bunch of us walk in, we're equal. So we can fight each other using a data MAC or some other protocol. What ends up happening here, the essential nature of what's going on is that the requirements at the data MAC level are less strict than the requirements at the sensing MAC level. And so the sensing MAC complexity dominates here. Because for data MAC, it's okay. Packets, they can collide occasionally. I just have to sense you, and you're usually nearby. I don't have to worry about too much shadowing to you if I'm going to actually muck around with you. But the primary is far away. There might be a hill or a building or God knows what in between. And I don't know. So I have to account for all that. And plus, the situation is different. I'm not supposed to bother him. Among us, we're sort of equal. I bother you, you bother me. A little bit's okay. But not to him. I'm not supposed to bother him except 1% of the time. It's this asymmetry which causes the trouble. Yeah?
So, in the figures of merit that you're showing, right?
Yeah.
What is being assumed about how the receivers of the primary are distributed? Or, effectively, it seems like that is sort of fundamentally the issue.
Yeah. So I assume
So
nothing.
All these figures of merit, right? Is there some assumption you're making about them?
Yeah.
that Sort of is,
I say I know nothing about where they're distributed. And so I must do... So everything here is like min-max, right? So I say, whenever I say I'm not modeling something, I'm going to say worst case over what I'm not modeling. So the worst case model is that wherever I am, closest to me in the protected radius is some primary receiver who's actually listening. That's the model. And that the shadowing is asymmetric, that I'm being shadowed while he's not. So the basic approach here, the paradigm that I'm proposing is, if you want to back away from that, you have to give a model. Have a model you can validate and say, over that model, I'm now going to take expectations or probabilities as needed. If you don't give me a model, you have to say, for all the unmodeled parts, worst case. Except you can also write off a certain percentage appropriately. We did that writing off when we said, this fraction we're just going to give up. This fraction of users. But that was well modeled because that was based on the distance attenuation. So that's roughly how the arguments here are going. At the end of the day, what all this is about, and I should just close here, is that, we want to, let me just skip all this. Yeah, maybe I'll just start off here. What we want to do is we want to say there's an old problem, robust operation of many different devices. We have this new consideration. We want to protect the primaries relative to the secondaries. Of course, markets have their own problems. Everyone's going to have their own problems. At the end of the day, you want to move from open loop guarantees of robustness to closed loop guarantees of robustness. You can't just say the robustness problem is solved. The way that if you stick within one model, the transmit power constraint, fixed bandwidth communication model, then yeah, the robustness problem is solved by the FCC. But you're now proposing something different, so you also have to solve the robustness problem. And if you want to do it in closed loop, you have to do the modeling. And that's essentially, and if you work it all out for opportunistic use, the net answer is it's a lot harder than it looks. Because all these things add up, and they cause trouble. And all this requirement for cooperation is just saying that cooperation is just a word for ad hoc infrastructure. Ad hoc infrastructure is just one kind of infrastructure. So now the question becomes, what kind of infrastructure do you need to support opportunistic use? So again, should we have police? Should we have UAVs flying around? How should we do it? So one speculation is that the existing providers might be in the best position to exploit this situation. So suppose secondary use is allowed. Verizon has bands for coordination, so they can coordinate among sensors. They have towers and base stations that they can use for sensing, which are going to be more well modeled with regard to fading and shadowing. On top of that, Verizon is very used to the idea of allowing more costly nodes to enable lots of cheap ones. And so Verizon can sell you the Verizon WCOG card, which coordinates with Verizon base stations for getting access to bands. And the robustness, Verizon takes care of the robustness and sells you a $10 card. While you could buy the New Brunswick city card, which coordinates with the city, which might do a lot more of the sensing itself. Or, point is that there are going to be other choices like that. Or you could just try to buy the ad hoc cognitive card, which doesn't coordinate with anybody except other ad hoc cognitive cards. And that's going to cost you $500 or $5,000. So it's your choice. And Verizon is used to things like this. And frequency agility is good for them anyway. Right? They can switch based on local availability, get access to more spectrum, and basically say, from Verizon's point of view, why should I pay $1 billion for the next license when I can use my infrastructure, just take it? It's not being used, I'll just take it. I'll be able to guarantee robustness to everybody. No one's going to want to take mine because I'm already using mine. So it's a win-win for me. So this is speculation. Basically, what it says is, if you want to be a band manager, you don't necessarily have to own the band. You just have to be able to sense reliably enough to guarantee robustness for the band. And I think the economists' approach of thinking of band managers as being a form of property rights sub-licensing is just wrong. There's no need for that. It's coupling two things together that don't need to be coupled. One does not need to be primary. So you don't need to own the national park to be a tour guide in the national park. Right? So there's a Disney model where you own Disneyland and you have tour guides. And there's a national park model where you have independent tour guides who give you tours in the national park. They don't own it. So when should a tour guide buy the park? Right? That's a separate question. Anyway, so that's...
So is it really true I could just walk into a national park and sort of get together a group of guys and start giving them tours?
Yeah.
Really?
Yeah.
You don't have to be licensed or certified by the park or something?
Well, I mean, there might be some state regulation. Yeah, of course, you might need, but... No, but it doesn't mean you have to own the park. It just means you have to be that you're not going to be the...
certified.
Yeah, certified that you're not going to muck around with the park. You're not going to take a bunch of people and say, okay, let's all dig here. Right? I mean, but that's it. You don't have to have ownership of it. So what this could say is that you have a group that says, I'm certified to robustly guarantee non-interference to primaries. Because I paid for the infrastructure, I'm going to coordinate, here's my protocol. But that's it. I don't need to own the band. So you can also sub-license away these bands the same way I can. We can compete to sell it off, and we have to be fair to each other. But at some point, maybe there'll be enough of us, and the bands will actually become congested, and then one of us will say, maybe I should just buy the band and kick you off and be able to guarantee better quality of service to my customers. But when I'm in the middle of nowhere, I'm saying, why should I bother buying any band? I can guarantee good quality of service because there's enough slack. So I think the entire model of saying that property rights are the precondition to having sub-licensing, or is just wrong. And the real question is best infrastructure trade-off cost. And that's the way that one should think about these problems. Okay, I've gone over, so I should probably stop. You guys ask good questions, though. It's good.
So you're also assuming that the secondary users are very nice guys and they don't hurt. I mean, they just respect the primary users and don't do anything, right?
I'm saying that's a requirement. We're going to say the requirement is you don't muck around with the primaries. Except to 1%, you must guarantee this appropriately. The point is there are lots of... And I'm saying that at some level it doesn't matter what you assume here. You have to assume something. And then see, the basic question is, under the assumptions you make, what are the trade-offs in moving from an open loop to a closed loop model of robustness? Because at the end of the day, the only way you're going to get better utilization is to move from open loop to closed loop. And whatever you do is going to involve such trade-offs. Okay. Thanks.